Okay, so today we'll continue with elementary theory of partitions. I mean, again, since all of us are familiar with partitions, so again, this will be a short lecture. First, I told last time, but I forgot to mention. So let me just show you Glacier's bijective proof, at least one side of Glacier's bijective proof for odd distinct theorem. Okay, so odd distinct theorem of Euler. So we are going to focus on odd parts. Okay, one side. So we are going to show that the number of partitions with odd parts is equal to the number of partitions with distinct parts, one side of the bijection. If the odd parts are distinct, then we don't need to really do anything. So we keep those in the same yeah. So sorry, I'm going to show the other directions where any distinct part is going to be right. So I mean, if any distinct part is odd, then I don't need to do anything. I just keep the distinct part as it is. Okay, so if a distinct part is even, then that part can be written as some odd into even number, right? Because any even number can be written as a odd number times an even number. So I mean, if it is 4, then we can just write it as 4 into 1. So 1 is odd here. Okay. Otherwise, 12 is just 4 into 3. So 3 is odd here. Okay. So we can always do this. So this actually allows us to break the parts. Okay. So for example, let's take the part 10. So 10 can be written as 2 into 5, and this allows us to break it into odd parts, 5 into 5. So suppose we have 8, then 8 is just 8 into 1, and this allows us to break us into odd parts. So that means any distinct part, we can just break it into odd parts. This is one direction of the bijection. So from distinct to odd, we can make any partition which is a distinct parts partition into an odd part partition. So what about the reverse direction? So in the reverse direction, we are going to club two parts together at a time. Okay, so for example, here we keep on clubbing until we exhaust the parts. So I mean, for example, here we in the first step we will club two of these ones together. So in 2 each will club together. Then this will become 2 plus 2 plus 2 plus 2. This is not finished because we can again still club 2 together. So we are going to club 4 plus 4. And again, we are going to club this together into 8. Okay. Now, suppose, for example, we had something like 3 plus 3 plus 3. So then this clubbing would result into 6 plus 3. And it would stop here because 6 plus 3 can be clubbed together. So this is the bijection in the other direction from odd to distinct. This is the map from the other direction from odd to distinct. So I mean, of course, I have not shown it very reversely, but from distinct to odd, I think it is clear. But from odd to distinct, you can take a look that this actually gives us a bijection. Okay, so this is the bijective proof that Glacier gave, and there are many other nice generalization. So, for example, one generalization is by Sylvester, which I think we'll see probably later on. But Sylvester's generalization is with odd distinct. Okay, so let me just state Sylvester's generalization, and I'm going to show one side of that proof. I'm not going to do the both sides. So Sylvester's refinement says that the number of partitions of n using exactly k odd parts, and each of these may be repeated, okay, equals the number of partitions of n into k separate sequences of consecutive integers. Okay. So what do I mean by this? So let's look at an example. So I mean, so one side is clear, number of partitions of n using exactly k odd parts. So if say n is 15 and k is 3, then one such example would be say 11 plus 3 plus 1. Okay, so this is an partition of 15 into exactly 3 odd parts. And if you are interested in repeated parts, then this can be so let's say this can be say 5 plus 3 plus 3 plus 3 plus 1. Is this correct? Yes. So here the part 3 is repeated, but there are exactly 3 different odd parts, 5, 3, and 1. Okay. Now what about the other side? Partitions of n into k separate sequences of consecutive integers. So one such example would be something like 6 plus 5 plus 3 plus 1. Is this right? Yes, because this is one sequence. 5 and 6 are consecutive numbers. 3 is one sequence in itself, and 1 is one sequence in itself. Okay, so this is an example of the other direction. So this is a refinement of Euler, because in Euler's partition we were not saying anything about the k. So if k is equal to 1, then yes. So if k is equal to the length of the partition, then this just gives us distinct parts partition. Okay, and in the other side, this will only give us odd parts partition. So this is a refinement of Euler's theorem in that sense. Now, what about the proof? So there is a nice bijective proof by Sylvester, I think Sylvester himself or Franklin, and this goes as follows. So I'm going to show for the odd to sequence case. Okay, so let's take a big example. So let's say 13 plus 13 plus 13 plus 11 plus 9 plus 3 plus 3 plus 1. Okay, so this is my odd partition into odd parts. So now I'm going to draw the Ferrar's diagram for this partition, but I'm going to draw it in a different way. So the first part is okay. So I'm going to just put 13 dots, 7, 8, 9, 10, 11, 12, and 13. But in the later dots, so I mean, since these are repeated, so I'll just put the repeated parts without any so repeated parts I'll just write as it is. Yeah, maybe I should have taken a smaller example. Anyway, so bigger example, it's nice to see. Okay, but now this 11, I'm going to justify it. Okay, I'm not going to start from here, but I'm going to justify it in the center. So that means I'm going to start from here, and I put 11 dots, one below the other. Okay, so I mean, I'm going to justify it in the central column. So 1, 2, 3, 4, 5, 6. So this is the central column, and I'm going to justify my partitions in the central column. Okay, so the 9 again, I'm going to justify it in this way. Okay, and 3, similarly, I'm going to justify it in the center. So this is a pictorial description of the partition. So now what I'm going to do is I'm going to draw a line. So let me use a different color. Okay, so I'm going to draw a line in the central column, and when I reach the top, I'm going to go to the right. Okay, and I do this for all of the lines that I can draw to the right. So I'll go to the top. When I reach the end, I'm going to go to the right. So this is just one. In the other direction, I'm going to do the same thing, but I'll go to the top and then I'll go to the left. Similarly, I'll go to the left here. Okay. And these lines will now give me the new partition, which will be the partition into exactly k separate sequences of consecutive integers. So let's see if we really get it or not. So I'll have to rearrange the parts so that they are in decreasing order. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the first part is 14. Then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then I have 11 as a part. Then 1, 2, 3, 4, 5, 6, 7 as a part. Then 4 as a part, 1 as a part. And in the left, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 as a part. Then I have 4, 8 as a part. Then 6 as a part and 3 as a part. So if I now rearrange this in decreasing order, so then I have, sorry, 12, 11, this is gone, this is gone, this is gone. Then I have 8, 7, 6, right? And then I have, sorry, 4, 3, and 1. Okay. So 4, 3, and 1. So in my original partition, I had 1, 2, 3, 4, 5 distinct parts. So 1, 2, 3, 4, 5 distinct odd parts. And in my new partition, I should have 5 separate sequences of consecutive parts. And I really have that because this is 1, this is 2, this is 3, this is 4, and this is 5. So I have 5 sequences. Now, this is actually a bijection between from odd side to the sequence side. So again, I leave to you to justify that this really gives a bijective proof of Sylvester's theorem. So this is this picture gives you the bijection. So you have to just justify that if you do this kind of drawing and rearranging the parts, then you really get different sequences of parts. Okay. Right. So this is one refinement of Sylvester's of Euler's theorem, which is at least not in this chapter in the book. I think it is probably in the later section of the book. Anyway, so let's come back to more generating functions for partitions, and we have a theorem now. So this is the generating function of partitions where the largest repeated part is k, largest repeated part is k, is given by, it's a very simple formula, is given by q raised to the power 2k over q square infinity and q square k. Okay, so we want to prove this, and the proof is okay. So let's do the proof. Okay, so I mean, I'll say something about the proof. Let's see. So parts which are larger than k are distinct because the largest repeated part is k. So any part which is bigger than k has to be distinct in the partition. So, and that is generated by minus q to the power k plus 1 q infinity. So all the parts greater than k are generated by this. And parts smaller than k has no restriction. So it can be bigger, it can be smaller. Oh, sorry, it can be repeated, it may not be repeated. So those parts are generated by 1 over q k minus 1. Okay. And the part k is repeated. So this part has to appear at least twice, right? So it has to appear at least twice. And that part is generated by this quantity. Okay. So that means the generating function for our partitions where the largest part is repeated, where the largest repeated part is k, is now just a product of all these three quantities. So this is for the part smaller than k. Then this is for the part which is equal to k. And this is for the parts which are greater than k. Okay. And this is now equal to, so q 2k minus qk plus 1 q infinity divided by qk. And now I'm going to simplify this a bit. So this bit is okay, k plus 1 q infinity q q k, and then I'm going to multiply above by minus q q k and divide it by minus q q k. Okay, so if I do that, this part and this part together, I can just club them, and this will give me minus q q infinity, and on the bottom I'll have q square k. Okay, and this is by Euler's odd distinct partition. So this is the generating function for distinct partition, and which is the same as the generating function for odd partitions. So I'll have q square infinity times q square k. So this is the proof for this generating function. Okay, right. This was a nice combinatorial argument to give the generating function. So I mean, you can also give theorems such as, so one Q series identity would be something like QQN, and this is equal to sum of k from 0 to n q to the power k QQK. So this part is the generating function for partitions into exactly k parts. Okay, and this is the generating function for partition into at most n parts. So if you just sum over the generating function for partitions into exactly k parts, where k is running from 0 to n, then you are going to get the generating function for partitions into at most n parts. So this is a nice combinatorial proof for this identity. Okay. Other type of identity that you can get is something like partitions into distinct odd parts is actually equal to the number of self-conjugate partitions. So what is a self-conjugate partition? I think you probably already know that if you have a partition and if you reflect this partition along the diagonal symmetry axis, then you get what is called the conjugate of a partition. Okay. So this conjugation is an involution. That means if you do the conjugation twice, then you get back the original partition back. So if a partition is equal to its conjugate, then that class of partition is called a self-conjugate partition. And another result is that the number of self-conjugate partition, again, the proof is quite easy, a combinatorial proof, self-conjugate partition is equal to the number of partitions into odd distinct parts. Okay. So how to make such a partition? So if you have, I'll give you a hint. So the hint is something like this. So there is a thing called hook length. Okay. So the hook length of a cell, suppose you have a partition. So suppose this is the position of the dot. Okay. Imagine that this is a Farrer's diagram and this is the position of the dot. The hook length of this dot is the number of dots to its right plus the number of dots to its bottom plus the dot itself. Okay, so for something like this, the hook length for this is 2 plus 1 plus 1. So that means it is 4. Okay, and for this, the hook length is 1 since there is nothing below, 0 plus 1. So the hook length is 2. Okay, so you have to work with hook lengths to prove this result. So this is left as an exercise. I mean, it's very easy. You can probably already see what is going on. So there is a theorem by Andrews and Deutsch, which I'm going to state. And this theorem states that, so you will see why we are doing this theorem. So there are exactly as many partitions of a positive integer n into k even parts as there are partitions whose largest repeated part is k. So we already know the generating function for the second bit, right? So we already know the generating function for partitions whose largest repeated part is k. Now it is enough to prove this theorem to show that the generating function for partitions of n into k even parts is exactly the same. So since the odd parts are unrestricted, we can just figure out the generating function for these even parts and then just multiply it with the odd parts, and we are going to get whatever we have here. So again, the proof is left to you. One part is already done. We already know the generating function for this bit. You just have to show that the generating function for the other bit is the same, and that is the easy part. Okay. So let's now go a little bit further and now try to see some proof techniques for power series, using power series. Okay, and we are going to prove a few results of Euler. So, I mean, one, we are going to prove a sort of generalization of Euler. Euler generating function for partitions. Okay, so the result that we are interested in proving is something like this. So this bit, this part, this is actually the generating function for partitions, where we are also keeping track of the number of parts. Okay, so for example, this part, which is inside the sum, this is the generating function for partitions into at most k parts. Okay, here x is keeping track of the number of parts. Right, so we want to prove this result. So I mean, the combinatorial proof is very obvious, so which is what I said just now, but we want to prove this using some Q series method. So this is the same thing as if I just replace x by xq. Okay, so I'm just going to replace x by xq, and this will actually give what I just said. So k goes from 0 to infinity, x to the power k, q to the power k, q, k. So the coefficient of x to the power k here is the generating function for partitions into exactly k parts. Okay, this was the coefficient for x to the power k in this is the generating function for partitions with at most k parts, and here the coefficient of x to the power k is the generating function for partitions into exactly k parts. And we are going to prove this. So the proof that we want to do will be reminiscent of one of the proofs that we saw last time, and that was to write one side as fx. Okay, so I'm going to write down the sum side as fx now, x to the power k, q, k, and I'm going to see what is fx minus fxq. So the objective is to find a sort of recurrence again. And this time the recurrence will be very short and simple. So this is k goes from 0 to infinity, x to the power k, k minus k going from 0 to infinity, x to the power k, q to the power k, k. Okay. So now this will be k goes from 1 to infinity, because the 0 term will get cancelled. So if k is equal to 0, then the first term here is getting cancelled with the first term here. So we can start from k equal to 1. So x to the power k will be factored out. So I'll have 1 minus q to the power k, k. And I want to write this as in terms of fx, right? So this quantity in terms of fx. So you'll see that 1 minus q to the power k gets cancelled with k. The last term will get cancelled. So this is something like x. So x to the power k minus 1, k minus 1, and k is going from 1 to infinity. So this is exactly fx. If you just make the change k minus 1 go to j, so this will be x to the power j, j, and now j will start from 0 to infinity. So this is exactly fx. So this is equal to x times fx. So now I have a nice recurrence. So this actually gives me that fx is equal to fxq over 1 minus x. Okay, and this in turn will give me fxq squared over 1 minus x times 1 minus xq, something like this. And I can just keep on doing this. So this will be 1 minus x, 1 over 1 minus xq, and so on up to fx to the power xq to the power n over 1 minus xq n minus 1. Okay. So this is just equal to fxq to the power n over x comma qn. Now let n tend to infinity, then this fxq to the n is going to actually f of 0 as q is less than 1. So if you look here, xq was this quantity. So this is just going to f0. Okay. And this is equal to 1. F0, if you evaluate, this is just equal to 1. So that means I have now that fx is equal to 1 over xq infinity. Okay. So this was what we wanted to prove. So this was a very nice and short proof of a nice identity of Euler. I mean, it is expected that the proof would be nice and short because the combinatorial proof is pretty simple, right? So can you hear me?
Yes.
Okay. So let's go to the next result, which is a finite version of Cauchy's theorem. And Cauchy's theorem is the result that we sorry, this is the finite version of Euler's theorem, and this will be the generating function sort of. Yeah, let me just state, and then you will see what I mean. So finite form, and this is by Cauchy. So here mod x mod q is less than n, less than 1, and n is a natural number like always. So I have 1 over xq n plus 1 is equal to k from 0 to infinity, n plus k, choose k, q, x to the power k. So you will notice that the coefficient of x to the power k is now the generating function for partitions into where you have this into at most n parts, and each part is at most j. So that was the result that we discussed last time. And this theorem, the proof is again similar, and we want to again write this as some, well, okay, not so similar, because we want to use some properties of power series now. So let me write this side as some generating function. Okay, so let's call this c and k q x to the power k. Okay, and k is going from 0 to infinity. So this coefficient will depend on q now. Okay. So from here, actually, we notice that if c and k q x to the power k q to the power k is nothing but, so k is greater than or equal to 0, is nothing but 1 over x q q n plus 1. I'm replacing the x by xq. Okay. Again, 1 minus x over xq n plus 1 is, so 1 minus x will get cancelled from here and here, and I'll be left with on the bottom I'll have xq q. It will end at n, but if I write n plus 1, then I have to multiply it by with something, and that is 1 minus xq to the power n minus 1. Oh, sorry, n plus 1. So in this case, I am cancelling out the last factor, and here I am cancelling out the first factor. So in terms of generating function, this is just 1 minus x sum of k greater than 0, c and k q x to the power k, which is equal to 1 minus x to the power 1 minus x q to the power n plus 1, c and k q x to the power k q to the power k. k is greater than equal to 0. So now if you just compare the coefficient of, well, let me just write one more step and then it will be probably clearer. Yeah. So, I mean, okay. So C and K, Q, x to the power K, I have 1 from this term. And if I bring the 1 times Q to the power K from here to the other side, then I have 1 minus Q to the power K. So this is greater than equal to 0. And on the other side, I have C and K, Q, x to the power K plus 1. So this term, minus x to the power K plus 1 will go on this side. And then this x will get multiplied with x to the power K. And I'll have 1 minus Q to the power N plus K plus 1. K greater than equal to 0. Okay. So we make the change of variable. K plus 1, I can just change it to some j. Then this quantity, well, I'll just keep it as k, okay? So you will understand. So k minus 1, k, x to the power k, 1 minus q to the power n plus k. Okay. And now we are in a position to compare coefficient. So here k will actually go from 1. And in this case also we can write k from 1 because q to the power 0 is just 1. So 1 minus 1 will get cancelled. So we can very well write this as k going from 1. Now if I just compare the coefficient of x to the power k from both sides, then from this side the coefficient of x to the power k is 1 minus q to the power k times c and k q. And on the other side, the coefficient of x to the power k is c and k minus 1 q times 1 minus q to the power n plus k. Okay, so we now have a recurrence, the starting point of our recurrence. And if we just keep on doing this, so from here we'll get c and k q is equal to c and k minus 1 q 1 minus q to the power n plus k over 1 minus q to the power k. So if you keep on doing this, so in the next step we'll have 1 minus q to the power n plus k minus 1 over 1 minus q to the power k minus 1. So this will keep on going and ultimately will end when k minus 1. So this goes down to 0. And on the top I'll have 1 minus q to the power n plus k times 1 minus q to the power n plus k minus 1 and so on until 1 minus q to the power n plus 1. Okay. And on the bottom I have 1 minus q to the power k and so on until 1 minus q. So what is Cn0q? And this we now have to figure out. So this was, yeah, so Cn0 is just the coefficient of x to the power 0. Okay. And this is just 1. So this is just equal to 1. Okay. So what is this? This is nothing but n plus k, choose k, q. Because on, so I mean, this is q n plus k over q n and q k. So the q k is already here. This q n plus k will cancel some of these terms, which will get cancelled with q n, and whatever will be left will be exactly this. So this is exactly equal to this. And this was the coefficient of x to the power k on the sum side. So we have proved that the coefficient of x to the power k is exactly equal to n plus k, choose k, q. And this is what we wanted to prove. So this is what we wanted to prove. Right. So there are other results by Euler. For example, I'm going to just state one, and the proof is exactly same. So on this side, I have minus xq, and this is now the generating function with exactly, sorry, with distinct parts, but where the number of parts is being kept track by this x. Okay. Yep. And this is equal to k goes from 0 to infinity, q raised to the power k choose 2 x to the power k q q k. So this quantity is the generating function with exactly k distinct parts, okay, one of which can be 0. So why we have k raised to the power k choose 2? So k choose 2 is nothing but k times k plus 1 by 2, okay, and this is just 1 plus 2 plus so on up to k, right? So if you have exactly k distinct parts, then each of the parts, since they're distinct, will contribute at least 1, 2, 3, and so on up to k. So this contribution from the distinct parts will give rise to q raised to the power k choose 2. Right. So I mean, the proof is again similar. So you write this part as some function, let's say fx again, and then you try to figure out what is fx minus fxq, and you will get something like fxq, and then there will be some factor. Okay, so this will give you the recurrence step, the first step of the recurrence, and then you just keep on going down, and eventually you will show that this fx is equal to minus xq infinity. Okay, so I mean, this is also actually sort of like I mean, this is sort of the infinite version of Rothe's Q binomial theorem. So if you remember, Rothe's Q binomial theorem was just minus xq, and this was equal to k from 0 to n, n choose k, q raised to the power k choose 2, x to the power k. So this was Rothe's Q binomial theorem. And if you compare these two results, then this seems to be like the finite version of Euler's result. So instead of infinity, we have n. So yeah, I mean, that's right. So that is actually almost the end of the chapter that we wanted to discuss. But there is one more result, and this is called the Cauchy-Krill series. So before going there, if you replace in in Euler's result, if you replace minus x by some ax, then you will get something like axq infinity is equal to. So this is just replacing in place of minus x ax. Okay, here then you will get something like j greater than equal to 0, q raised to the power j choose 2 minus a raised to the power j x raised to the power j over qj. Okay, and again rephrasing. So if you have 1 over bxq infinity, so if you go up, and this was another result of Euler that we started with, so 1 over xq infinity. Instead of x, if I just have bx, then I just need to change the x to the power k here by bx whole to the power k. So this 1 over bxq infinity will just be again a sum j greater than equal to 0, b to the power j, x to the power j, j. So one result that Euler missed was what is the what is axq infinity divided by bxq infinity? Can this be written in terms of some generating function or some power series? And that was found by Cauchy, and I think independently also by Krill, and that is the result that we are going to end with today and also this chapter. So again, we need mod of q less than 1 and mod of bx less than 1. Then the result as stated is axq infinity divided by bxq infinity is can be written as this power series. So n goes from 0 to infinity, b minus aq n minus 1, b minus aq n minus 2, and so on up to b minus a x to the power n divided by qqn. Okay, so I mean this part this part should remind us of Rothes q-binomial theorem, which is here already. So which is here already. Okay. So minus xqn, if you, I mean, instead of minus xqn, if we write xqn or bxqn, then we'll get something like this. Okay. Instead of so we'll get something like this here. So we have to use Rothes q-binomial theorem to prove this. So I mean, the proof is not difficult. So you just need to multiply these two series. Okay. So just multiply, say 1 and 2. If you just multiply 1 and 2, then you are already getting the left hand side, and the right hand side you just need to use Cauchy's product of two infinite power series is another infinite power series, and the coefficient of that infinite power series is given by Cauchy's theorem. So I mean, that's, yeah, so we have already used this once. So if you do that, you will get something. The coefficient, you will get something which should remind you of Rothes q-binomial theorem, and then we use Rothes q-binomial theorem to get this form that we wanted. So as expected, this gives, as corollaries, this gives both Euler's and Cauchy's result. And there is also a partition theoretic interpretation for this, which we'll see later on. But this actually finishes the elementary theory of partitions, which is chapter 3. So I have skipped section 3.8, which is not required later on, but we can do this when it is. I mean, I think it is required only in chapter 7. So when it is required, we can do this. So that's all for today.